Hello everyone, this talk is about a refined comprehensive earthquake focal mechanism catalog for Southern California, derived with deep learning algorithms. Earthquake focal mechanisms are primary data for analyzing fault zone geometry, fault slip direction, and the crustal stress field. Traditional method uses the recorded P-wave first motion polarity and the S-wave P-wave amplitude ratios to inverse the earthquake focal mechanism. But for small earthquakes, the phase arrivals and the polarities are hard to be separated from the noise. We overcome this challenge by implementing CNN polarity picker and phase picker that are trained using millions of seismic waveforms in Southern California with high accuracy and high detectability. We applied the improved procedure to all catalog events from 1981 to 2019. More than 40 of the events have at least one additional S-wave P-wave amplitude ratios and one additional P-wave polarity, leading to 42% more focal mechanisms than the standard catalog. Most of the improvements are from the small magnitude earthquakes and the quality B and C focal mechanisms. Before 2007, there were at least 20% more focal mechanisms obtained every year. After 2007, there were at least 40% more focal mechanisms obtained every year. To check the quality of the new catalog, we first compare it with the standard catalog and find that they are very consistent. Compared with the standard catalog, the new catalog is more consistent with moment tensor catalogs solved using waveform inversion methods. And the repeating earthquakes share more similar focal mechanisms in the new catalog compared with the standard catalog. Here are the map views of focal mechanisms in Southern California and Northern Baja California. Our new catalog delineates more details in space and time. So what's new we can find from this new catalog? Let's first look at the Salton Sea geothermal field. We first compare the temporal variation of net production volumes in the Salton Sea geothermal field, which is this black curve, with a percentage of reverse faulting events in the same region, which is a blue curve. The color bar shows the correlation coefficient between these two curves. The new catalog shows a strong correlation between net production rates and the percentage of reverse faulting events, which might suggest that the reverse faulting events are mainly due to the change of overburden pressure caused by the change of the net production rate. We further check the temporal variations of the focal mechanisms near the 2010 ML Kukapa earthquakes along AA prime. The upper figures show the focal mechanisms colored by p-axis azimuths. The lower figures show the faulting type. Before main shock, these two catalogs share a similar pattern, with mainly north-south, north-northwest, south-southeast oriented p-axis, and mainly normal faulting events. After the main shock, the new catalog show more northwest-southeast oriented p-axis near the Sierra Kukapa fault zone, and more reverse faulting events, suggesting more significant stress rotation after the major rupture. The new catalog also provides new insights in the fault zone structure. We checked the nodal plane orientations of focal mechanisms in the southern San Andreas fault zone. The new catalog shows less north-south oriented nodal planes and more near vertical nodal planes compared with the standard catalog. To sum up, we obtained additional rivals and polarities using CNN pickers, resulting in 42% more focal mechanisms with higher quality compared with the standard catalog. The new catalog provides new insights to the stress regime, trigger mechanism, and fault zone structure in Southern California. Thanks for your listening.